Let's talk about finding eigenvalues on a TI-83 or TI-84. We can use the TI-83 or TI-84 to find the eigenvalues of a square matrix. Let's do this for the matrix A equals 4, -1, 6, 2, 1, 6, 2, -1, 8. First we press on, great way to start, and then we press matrix. Notice that matrix is in blue and it's above the X inverse key, so we access that first by pressing second. That's the way we access all the functions that are in blue on the calculator, and then by pressing the corresponding key, namely X inverse. So we get the matrix features. And we need to choose edit, so use the right arrow and scroll over to edit, and then scroll down to the name of the matrix. I think A is fine, so we'll just go with that and press enter. Enter the dimensions of the matrix. In this case, it's a 3 by 3 matrix. Remember, rows by columns. 3 rows, 3 columns. Enter the elements of the matrix row by row. So 4, enter. -1, enter. Don't make that a subtraction sign. It's got to be the negative sign, otherwise you'll get an error. 6, enter. 2, enter, etc. Now we're going to press Y equals. That's this button on the calculator. Well, first you need to press quit. So press quit and then press Y equals. And then you enter this complicated expression. But again, it's worth it, and you can do it. You're smart enough. By golly, you can do this. So enter determinant. That's under matrix math. Then A, that's under matrix names. And then the X, that's probably the XT theta button on your calculator. Identity of 3, that's the 3 by 3 identity matrix. That's matrix and then math. And then you press graph. You might need to press enter first, but press graph. And you end up with something that looks like this. Okay, this is cool. So based on this, we can see where the zeros of that determinant are, which means that we can see where the eigenvalues are. So if you want, you can see that they're at 2 and they're at 9. But if you're paranoid, you want to be more precise, you can find exactly where those are. So what you do is press calc, that's a second, and then trace, and then you choose 0 and press enter. Use the arrows to go to the left of the 0, press enter. Use the arrows to go to the right of the 0, press enter. And then use arrows to go near the 0 and press enter. That's the way you find the zeros on the graph. So the zeros of the function you will find are indeed 2 and 9. So the characteristic polynomial must be lambda minus 2 times lambda minus 9, because those are the zeros of the determinant. Just kidding. That's not the characteristic polynomial. The characteristic polynomial turns out to be negative lambda minus 2 squared times lambda minus 9. And how on earth can you look at this graph and see that those are going to be the eigenvalues, or that that's going to be the characteristic polynomial? Okay, first, you can tell that lambda equals 2 is going to be an eigenvalue of even multiplicity, because this graph doesn't cross the x-axis. Instead, it bounces. And when that happens, you've got a root, or a 0, of even multiplicity. So it's got to be lambda minus 2 squared. And then we can see that the graph crosses the x-axis here at 9, so it's going to be a 0 of odd multiplicity, or an eigenvalue of odd multiplicity. So we know, based on that, that it's got to be a 2 and a 1 over here, because it's only a 3 by 3 determinant. So you're not going to have a 0 of multiplicity 4 over here. This can't be a 4. This has got to be it's got to be a polynomial of degree 3. So if this is even and this is odd, that means this has to be 2 and this has to be 1. And you can also see that this is not going to be lambda minus 2 squared times lambda minus 9, because it doesn't go like this. Instead, it goes like this. Okay, so it starts up high and then goes up and then goes down low. So that's got to be a negative lambda minus 2 squared times lambda minus 9. So we can see that the eigenvalues are going to be 2, 2, and 9.